Welcome to our lesson on compositions and inverses. Now, I want to start off by giving an overview of the entire unit of material here. And this is important, and we're going to continue to do this with each subsequent lesson. So we can kind of say, all right, where are we at and where are we going with this? We've got to do some build up. This whole unit requires some build up to get to some really interesting problems that we can then solve. So what's going to happen here is we're going to start off talking about some basic function operations. And when you hear operations, you should think addition, subtraction, multiplication, division, which we will cover. And there's actually another operation we're going to deal with when it comes to functions, and that's going to be called compositions. Understand what a composition is necessary to understand what an inverse is. And that's the next section that we're going to get into. And so when we talk about inverse functions, rough ideas, an inverse function is a way to say, how do I undo a function? And when I use that word undo, that should hopefully click something in your memory bank about solving equations. That when you first learned how to solve equations, you started learning about undoing what was done. To say, all right, if there's addition that happened, how do I undo addition? I do subtraction to both sides. If there was multiplication, how do I undo that? I do division. And that's exactly why I want to explore inverse functions, is to say, in general, how can I solve an equation? If I can identify the function that's being applied, can I come up with an inverse function that undoes that? And so we're going to talk about inverse functions. We're then going to get into exponential functions, which have a ton of real-life purposes. So exponential functions are going to come up anytime that every step that you take in time, you multiply your previous value by something. And so this is going to come up in interest situations, in population growth, which can happen in microbiology, for instance, like bacteria growth. It can happen in the bigger sense of biology, like population growth in the sense of deer or mammals of different types. Can come up in lots of situations. Exponential decay also happens in half-life. It's how your body gets rid of toxins is through an exponential function. So there's tons of real-life purposes for which exponential functions come up. And so we're going to cover a couple sections on that, and then we're going to say, well, okay, since these come up in so many real-life applications and real-life situations, how do I solve these equations? How do I undo an exponential? So we're going to define the inverse of the exponential, which is what we end up calling a logarithm, which is just a name we give for the inverse of the exponential. But that's something I want to make sure that we're aware of early on, and I want to go over this overview here, is that exponential functions are somewhat intuitive, somewhat reasonable to deal with, and logarithms, if you just approach them independently on their own, logarithms seem like they're this brand new thing with their own set of rules that you got to memorize, but it's not really the case. If we understand what an inverse is and we understand what an exponential function is, then the logarithm is just the inverse of the exponential. And you'll be able to figure out the rules for them based on those two facts, that we know something about the exponential, we know something about inverses. So we're going to talk about those rules and how to derive them from the inverse of the exponential. We're going to do some calculator work, and finally we're going to get to the real meat of the matter. We're going to be solving exponential and logarithmic equations, some of which are coming up in real life situations. And so that's our overview for the entire unit, our game plan for the next couple lessons. So I'm going to get right into our operations with functions. We're going to talk about adding, subtracting, multiplying, and dividing with functions. And I'm going to go through this relatively quickly because it's very intuitive. It's pretty much exactly what we'd expect. That if I want to take these functions f and g, and I want to say what is the sum of f plus g of x, then literally what I'm going to do is I'm going to take f of x and add that to g of x. F of x in this case is defined as 3x plus 2. G of x is defined as 7x minus 5. And this really just turns into a combined like terms situation. And so it should be very straightforward, very simple for addition. Now for subtraction, if I want to subtract f minus g, this should become, as you'd expect, f of x minus g of x. The only kind of trick, the only thing to be aware of in this case is to remember to subtract all of g. So by subtracting all of g, we're saying make sure you have parentheses around g, which basically means distribute that negative, and then we can combine like terms. So pretty straightforward, pretty simple. As we get into multiplication and division, same idea. F times g would be f of x times g of x, where f of x was 3x plus 2, g of x was 7x minus 5. And so it becomes just a FOIL situation. I'm multiplying a binomial times a binomial here. So my first is 21x squared. My outside is negative 15x. My inside is 14x. And my last is negative 10. And then I would just combine like terms. And that's multiplication. Now, division is actually even easier. So division says let's take f of x, divide it by g of x, where f of x was 3x plus 2, g of x was 7x minus 5, and really that's it. If this simplifies, great. We'll go ahead and try to factor the top, factor the bottom, see if there's a common factor. That's all well and good. Now, one thing that we should probably specify is we probably should remember that whatever is in the bottom can't be 0. So we probably should say something along the lines of, hey, this is the quotient, this is what I get when I divide. Just remember that your bottom can't be 0. So x can't be 5/7. So the one thing I want to say just as far as your own studying when it comes to these operations with functions is don't forget to review this before the exam. This material is really, really easy. And we're going to deal with something that's a little more complicated called the composition. Composition looks very similar to multiplication. It's f of g of x. So that's the composition right here. And we're going to talk about that here in just a moment. But I want to point that out just in terms of making sure that you do study this and remind yourself, oh yeah, there was this thing called multiplication. Because if you get a multiplication problem on the exam, it should be gimme points. And if you accidentally do composition instead, you're going to get it wrong, and that's going to suck to miss those points. So just make sure you're careful with remembering that these things exist and to remind yourself before the test. So let's do a little review of what it means to be a function. So oftentimes you're taught that a function is kind of like a machine, that there's some sort of input into the machine, that there's some x value coming in. The function f does something to it, and the output to that is the y value, or f of x. So we input the x is what goes in, stuff happens, and we get an output. So a function could be x squared. So we can say, give me a number, that's my input, I'm going to square that number. Whatever the square of that number is, that's the output. So that's an example of a function. What we want to look at now is we want to look at what's called a composition of functions. We want to say start with that x value, plug it into my function, get an answer, but then plug that answer into a different function. The output to that is g of f of x, which is sometimes written g of f of x. Either notation is fine. So if we think about a function like a machine, then a composition of functions is kind of like an assembly line of functions, of machines. So with this assembly line, we take a value, we plug it into one, we get an answer, we take that answer and plug it into the next, kind of like an assembly line down at Ford. So if you went down to Ford, you'd start off with some parts, stuff would happen to them, more parts would get added in, the results of that go up the line, more stuff happens, some welding gets done, whatever, the results of that go up the line, and stuff keeps happening at every step of the way. And that's what a composition of functions is. We start with some sort of value, we plug it in, we get a result, we take that result and plug it into the next function and go from there. Now we do want to pay attention to the order that things happen in here with the way I have this written. So notice that we work from the innermost parenthesis out. So if I have g of f of x, x is what we start with, then f happens to it, then g happens to it. So written in this other notation, you can sort of think about it as the x goes from right to left. It starts at x, it hits f next, the answer to that hits g next. So we're going to look at some things we can do with compositions. We're basically going to break this down into 3 different types of problems. We're going to look at problems where we do a composition where we start with a number, plug it in, get an answer, plug that number in, and we'll end up with a number. Another type of problem that we'll deal with is to start off with an x, plug the x in, get some sort of expression, plug that expression into the next function, and end up with an expression. The third type of problem we'll do with compositions is to go the opposite direction. We're going to start with an answer and try to say, what were the functions that composed this? Where did these come from? So that's kind of a process and where we're going from here. So in this example, I want you to notice that we are starting with a number. We're starting with a number. We're going to plug that number into a function. When that happens, our answer should be another number. We're going to take that number and plug it into the second function, which should result in a number. And so the big thing that I want you to see here is that if we start with a number, our final answer should be a number. So when you plug a number into a composition, the final answer will be a number. Let's look at how I want you to solve this. The first thing that I would do if I were you is I would rewrite this original problem f of g of 2 into a little bit different notation. It means the exact same thing, but I'm going to write it as f of g of 2 with parentheses. And the reason I like to write it like this is because with parentheses, I know how to handle them. I know how to work from the innermost parenthesis out. So the innermost parenthesis is a 2. So I start with a 2. As I go out, what I have written in blue there, g of 2, is the next thing I actually want to do. And I'm actually going to do it off the side a little bit. So if I want to know what g of 2 is equal to, then that says look at my g function and just plug a 2 in. That's what g of 2 means. So it means 2 squared minus 1, which is 4 minus 1, which is 3. G of 2 is the same thing as 3. So I can replace that g of 2 with just the number 3 because it means the same thing. Now the problem that I'm trying to solve is f of 3. So if I'm doing f of 3, that means f says 2 times whatever you plug in minus 3, and what I'm plugging in is 3. So that's going to get me 6 minus 3, or 3. And so again, I started with a number. My final answer is a number, and that's what we should expect. That's what we should look out for. Now I want to look and say, well, what if I reverse the order? What if instead of doing f of g of 2, what if I did g of f of 2? Will I get the same answer? Will I get a different answer? Well, let's check it out. First thing I'm going to suggest doing is to rewrite this problem in that parenthetical notation, g of f of 2. And then off to the side, we can talk about what f of 2 is. F of 2 says look to the f function and plug 2 into it. That's going to get me 1. F of 2 means the same thing as 1. So that means my original problem over here was really asking for g of 1. The g function says whatever you're plugging in, square it, and then subtract 1. What I'm plugging in is 1. That gets me 1 minus 1, or 0. So when I changed the order that I did these functions in, I did get a different answer, which should make sense if we go back to our idea of an assembly line. If you go down to Ford and you flip the switch and send the assembly line in reverse order, it's obviously going to change what happens. So we got to start with stuff that are a little more rough first, then do some of the finishing touches later. If you start off with the finishing touches, that's going to be messed up. So we know that most of the time, if you change the order of the composition, you should get a different answer. So now we're going to look at the second type of problem that we'll solve when it comes to compositions. So in these problems, instead of starting with a number and ending up with a number, we're going to start by plugging an x in. So instead of plugging a number in, we're plugging in this variable x. And when we plug a variable into a composition, the final answer will be an expression. We should end up with something in terms of x. We shouldn't end up with just a number, usually. Let's look at how we solve this, and really we're going to solve this in pretty much the same way as what we did when it came to the numbers that we were plugging in. We're going to start off by saying, let's rewrite this in the parenthetical notation f of g of x. Now, in some senses, our next step is going to be even easier, because previously we solved for g of whatever that I have written in blue. But in this particular problem, we actually know exactly what g of x is. It's given to us. It's given to us as negative 2x plus 5. So there's nothing really to solve for. Now, the only hard part now is to make sure that we understand what's going on here. So what I want to do first is I want to look and say, well, what if I didn't have that stuff in blue? What if I just said f of blank? What is the f function telling me to do? So if I look up at the f function and say, instead of f of x, what if I just had a big blank here? Well, that function f is saying 3 times whatever that blank is plus 1. That's what the f function is saying, and that's how I want you to see that f function. When you look at 3x plus 1, I want you to realize that we plugged x in. So if I don't know what I'm plugging in, it's just 3 times blank plus 1. But in our problem here, I know what it is I'm plugging in. I'm plugging in negative 2x plus 5. So as far as our function, I'm plugging in negative 2x plus 5. Once I do that, now it's just a matter of simplifying. I can distribute my 3 to get negative 6x plus 15, and then I can combine like terms. Now, to make sure you understand what it is that you've actually done here, you've came up with a formula. You've come up with a formula for f of g of something. So that if I were to say, hey, what's f of g of 0? You could plug the 0 in here to negative 6x plus 16 and say that's what f of g of 0 is. It's 16. Or if I want to say what's f of g of 1, you could plug it into this formula. So you've combined all the steps of the composition that we did in the previous example into one step, one expression. Now let's go ahead and change the order and just see how that changes things up. So if I do g of f of x, then I'm saying g of, well, f is 3x plus 1. And now I want to say, what's g telling me to do? G is telling me to do negative 2 times whatever you plug in plus 5. So again, look up at what g of x says, and anywhere where there's an x, just replace it with a big fat parenthesis. Now that we have written down what g is, we say, well, I was actually plugging in 3x plus 1, so let's do that. Now it's just a matter of simplifying. Distribute that negative 2, and then combine like terms. And there's g of f of x. I'm going to step it up a little bit by looking at some examples that involve some squaring, so we can kind of see some other stuff going on, as well as an example where one of the functions has x in 2 places. So the first example here, we're looking at g of f of x. So again, order definitely matters. And we're going to start off by rewriting in the parenthetical notation g of f of x. So f of x in this case is x plus 4. And in this case, the g function is saying, whatever you're plugging in, square it, and then add 1 to it. That's what the g function is telling you to do. So remember, anywhere where there's an x in the problem, we should replace it with a big fat parenthesis. Now in our specific problem here, we're plugging in x plus 4. So now it's just a matter of simplifying this algebraic expression. That's going to give us x squared plus 8x plus 16 plus our 1. And then we'll combine like terms. And that's the expression that we get for g of f of x. Now the second part of this example, we want to do g of f of x again. So again, that's going to be g of f of x. Now in this case, f of x is 2x minus 1. Now in this case, for g, we're going to replace each x with a big fat parenthesis. So that means whatever I'm plugging in, I'm going to square it and then add 2 times it. That's what g is telling me to do. So that, for instance, if we wanted g of 5, we'd plug 5 into both x's. In this case, we're plugging in 2x minus 1. So we're going to replace each of those x's with 2x minus 1. And then again from here, it's just going to be a normal algebraic simplification. We're going to do some squaring, so we'll do a squared plus 2ab plus b squared. We'll distribute the 2, and then we'll combine like terms. Now we could go ahead and write this in a factored form if we really want to, but I don't really see any benefit in doing so. And so there's our answer. Now we're going to look at the third type of composition problem that we're going to deal with. And that's where we start with the answer, we start with the end of the composition, and we say, what are the components? What makes up this function? So when we're trying to find out the components of a composition, we're going to have something of the form f of g of x, where f and g are the components. So these guys are the components. And the actual answer is the composition. But that's what we're starting with. We're starting with the answer. We're starting with the composition. So as we're looking at this, what I want you to realize, if we look back to all the examples of compositions we've already done, is when we rewrite this as f of g of x, we start here, then we go there, and the last thing we do is that f in this case. So the outermost function that we deal with is what I'm going to call the main thing that's going on in this problem, because the last thing we do. So in terms of order of operations, it's the outermost thing that's enveloping this whole thing. It's the main thing. Now the innermost function, the innermost component, is what we plug in to that main thing. So that's how I want you to view this in a general sense, is that the outermost function, which in this case is f, is the main thing going on, and what we're plugging into that is the g. Let's look at actually solving this example then and determining what the f of x and g of x are. So what I want you to do to solve this example is I want you to put your thumb over a portion of the problem. Now you can't see my thumb, so I'm just going to kind of cross it off. I'm going to put my thumb over the x plus 2 in this problem. And I'm going to say, what is this? What's left when I put my thumb over a portion of the problem? The main thing that I see left in this case is something is being squared. So remember that my main thing is the outermost function, and so f is saying something is being squared. But I'm being asked, what's f of x? Well, that would be x squared. So to answer the question of what's f of x going to be, it's x squared. Now the innermost function is what is plugged in. So what's plugged in is what we had covered up. So what is it that I'm plugging into the squaring? I was covering up x plus 2. And that's how we're going to solve this. That's how we find the components of this. We're going to cover up a portion of it that includes the x and say, what's left? What's going on here? That's my main thing. And then what was that I was covering up? That's the innermost function. Simple as that. Now, as we look at example 6 here, I do want to point out that there's not always a unique answer to each of these problems. So we can actually come up with multiple answers to this particular problem. And I'm going to actually walk you through a couple of those. So we're looking for f of x and g of x so that f is the main thing going on, and g is going to be what is plugged in. Or you can look at it as what did I cover up with my thumb. So if I cover up a portion of this with my thumb, I could cover up the 2x plus 3, for instance. So that's my g of x, is the 2x plus 3. So what's left when I cover that up? Something cubed plus 5. And so if I'm doing f of x, that would be x cubed plus 5. So that's one way that I could actually solve this particular problem, and those are valid components to that composition, and that would work. But then I could go kind of either direction with this. I could say, well, what if I didn't quite cover up as much? What if I just covered up the 2x? And then I said, well, what's left when I do that? Something plus 3 cubed plus 5. So that would be x plus 3 cubed plus 5. That works too. That's a correct answer. And I could go the other direction too and say, what if, instead of covering up 2x plus 3 like I did originally, what if I covered up a little bit more? What if I covered up the 2x plus 3 cubed? So 2x plus 3 cubed is what I covered up. What's left when I do that? Something plus 5. So x plus 5. Each of these 3 different columns I have are valid answers to this problem that says find the components f and g so that my original problem can be written as f of g of x. Now this is important because there's different reasons, different purposes for what we're doing here. One is, of course, just the simple problem solving to say, all right, what are the steps? What are the pieces that make up the whole, which is a good problem solving technique. Now, also later on, if you go on to calculus, there's times where you want to do some calculus operations. Won't get into the specifics of what they're called. You know how to do it with an easy looking problem, but as they get more complicated, you don't know how to do it. So if you can break it up into 2 easier looking problems, like what we have here, then maybe it's going to be easier to solve the calculus problem. And that's what we end up using this for later on in math. We break up complicated problems into its pieces, into simpler parts. Let's do one more example about compositions before we change gears. Now this particular problem, the way it's written, says here's all these possible components, F, G, H, and J. Let's write capital R of x as a composition of these. What's going on here is that this is sort of a multiple choice type problem. then I know my answer is either going to be f of g, or maybe f of h, or maybe f of j, but maybe it could also be g of f, or g of j, or g of h. We've got a whole bunch of possibilities. There's 12 possibilities to be exact. So there's a lot of multiple choice options here, but that's kind of what's going on here. If we want to make this a little bit easier, what we could do is look at this problem and say, which ones don't belong? I've got an absolute value. I've got a 2x plus 3. So it looks like G and J are probably the right problems going on. So then we got to say, well, is this problem going to be G of J of x, or is it going to be J of G of x? Which one is it? Well, this boils down to what's the main thing versus what's plugged in. So is the J the main thing and the G what's plugged in, or vice versa? So if I were to put my thumb over a portion of it, the thumb or the plugged in was the 2x plus 3. So that means the main thing, or what was left, was the absolute value. So if we look back and say, all right, well, if the main thing was the absolute value, that was the J, this must be the right way of going about it then. So that's how I would approach it. I'd approach it like a multiple choice problem here and just say, all right, which two are the functions that are actually going on here? Write it in either order and figure out which order is the right way by saying what's the main thing going on. All right, so now we're going to change gears a little bit, and we're going to start working towards our understanding of what an inverse function is. In order to understand what an inverse function is and to understand if an inverse exists, we have to define this property of functions called being one-to-one. So I want to remind you that what a function is, that a function is a type of relation that for every x in the domain, there corresponds at most one y in the range. There's your fancy definition. But remember, really what this means is it passes the vertical line test. What's bad for a function, for something not to be a function, is when there's a given x value with two different y values. So this is when it fails the vertical line test. That's bad for a function. The definition for one-to-one is if for every y in the range corresponds to exactly one x in the domain. So to put that in simpler terms, what that means as bad is we don't want to have two different x's that have the same y value. In other words, we don't want to have a horizontal line that hits 2 points of our graph, 2 points of our function. And so to tell if a function is in fact one-to-one, we have what's called the horizontal line test. And this is just like the vertical line test for functions. If you remember, the vertical line test for functions says, look at every possible vertical line. If any vertical line hits my graph in 2 or more places, this thing's not a function. The horizontal line test tests whether something is one-to-one or not. You look at every possible horizontal line, and if any horizontal line hits your graph in more than one spot, so if you hit your graph in 2 or more spots, it's not one-to-one. And you'll notice the notation I use for one-to-one over here. This is standard notation. 1-1 is notation used for one-to-one. So let's look at a couple examples of determining whether something is one-to-one or not. So if we think about being one-to-one in the horizontal line sense, let's actually skip down to the graph, because that's the easier one to start with. So if we look at a horizontal line that hits our graph in 2 places, then we can quickly say, no, this is not one-to-one because a horizontal line hit it in 2 places. So then we can look and say, okay, well, what does that mean in terms of ordered pairs? So if I look at some ordered pairs, like negative 6, 2 and 2, 2, those are what caused the problem that made it not 1 to 1. And so what should jump out at us is that we had the same y value occur. So if I want to test whether that list of ordered pairs up there is 1 to 1 or not, then I'm going to start off and say, all right, I got a negative 4. Is anybody else a negative 4 for my y values? Nope. We're all good there. So let's step it up to this 3. Any other 3s? Nope, no other 3s that are y values. So then we just keep on going. And we say, all right, how about a 4? Not a 4, not a 4, not a 4. How about the 8? Not an 8, not an 8. 11? Not an 11. So none of my y values match. Because none of my y values match, I can say, yep, that guy there is a 1 to 1 function. Now I should be checking to make sure none of the x values match too, because that would make it a function or not a function. But in this case, we can say, yep, none of the y values match. They're all unique. That's good. But in the second graph with the horizontal line test, we could see, oh, well, not all of those y values are unique. I did get a couple y values more than once. All right, so now we're going to get into the whole idea of an inverse. We're going to define an inverse. And I'm going to kind of go one step at a time here. I'm going to start off with a general graphical interpretation of what's going on, then try to give you a nice, straightforward, simple definition. Then we'll get into a little more complex definition. So what I want to start off with is I want to start off thinking about how we've sometimes visualized just a regular old function in the past. So we've got this pool of allowable x values that we can have for whatever's going on. This is called the domain. The domain is your allowable x values. The way we typically think of a function is to say the function f takes that x value over there and does something to it, and we get a y value out of it. Now this is the domain of my function f. This over here are the y values, or the range of my function f. And this is one way to visualize what's going on. We take a single x value from your pool of possible x values, we do something to it, and it becomes a y value. That's the function value, is the y value. Now the basic idea of an inverse is that we want to undo this. So visually what's going to happen is to say, I want to be able to take that y value and bring it back to where it came from. Now the notation that we use for an inverse function is it looks like we're raising it to the negative first power, but literally this is read as f inverse. It's not read f to the negative first power, even though the notation for it looks like it's f to the negative first power. So it looks like what's happening here is that that inverse function is going to take that y value over there and turn it back into the x value that it came from. That's the hope for an inverse. Now, if we look at our blue line, it started off over in this right blob. So that means that's the domain of my inverse. It's what I'm allowed to start with. And what I end with on the inverse is going to be its range. So this picture here is helpful. It's going to help us understand some of the stuff that's going on as we start to look at the wordy definitions. So as far as the wordy definitions are concerned, a function typically sends an x value over to a y value. And since an inverse is supposed to undo that, then it's going to send the y value back to the x value that it came from. So in other words, the function says my input is x, my output is y. The inverse says, let me take that y and send it back to x. My input is the y, my output is the x. That's kind of what's going on with these inverses. Let's make it even more wordy. The inverse of a one-to-one function f is the one-to-one function f inverse that consists of all the ordered pairs yx where xy belongs to f. That's basically what we just said in that simple definition previously, is if xy was on the function f, then yx is on the inverse. That's what we want to think about this as. So if I had a function that consisted of the ordered pairs 1, 5, 2, 8, 3, 11, and 4, 14, then his inverse is going to have 5, 1, 8, 2, 11, 3, and 14, 4. We're just going to flip-flop each ordered pair. That's all the inverse is. It says, hey, if I had xy on the function, then I got yx on the inverse. So in this particular problem, the domain of my function f, or my x values that I had, were 1, 2, 3, and 4. The range of it, the y values, were 5, 8, 11, and 14. But notice that 1, 2, 3, and 4, those values are the range of f inverse. 5, 8, 11, 14, those are the x values, or the domain of f inverse. And that's exactly what we saw in the original picture with the blobs, is we saw that the domain of the function and the range of the inverse are the same. Similarly, the range of the function and the domain of the inverse are the same. And lastly, when you take the composition of the function and the inverse in either order, you get back to where you started. Let me go back to my blob picture to write this out in symbols. So if we do the composition that we start with f and then we apply f inverse, we get back to where we started. So that means if I start with x, then I apply f, then I apply f inverse, I should get back to where I started. Similarly, if I go the other direction, if I start with x and I apply f inverse, then I apply f, I should also get back to where I started. This is the whole point that's going to allow us to solve any equation that uses a one-to-one function. So if we have a one-to-one function, we can solve it by applying the inverse. Because we can say, hey, if x had this function applied to it, and I want to get x by itself, I want to solve for x, just apply the inverse. And really, you've been doing this for years. Because if you were given the function x plus 2, and you knew that function was equal to 5, then you could say, let me apply the inverse function of plus 2. What's the inverse function of plus 2? It's minus 2. Let me apply that to both sides of the equation in order to get x by itself. Now, we didn't use those exact terms, but that's exactly what was going on. We had a one-to-one function that was blank plus 2 that we wanted to undo, and so we applied its inverse, which was blank minus 2. And we did blank minus 2 to both sides of the equation, and that solved the equation because it got x by itself. I want to bring that up because that's the big picture of where we're going with this. We're going to be introducing the exponential function that has lots of real-life purposes, and guess what? It's one-to-one. Then we're going to say, how do I undo that? How do I solve it? And we're going to apply an inverse. So we're going to define the inverse to be the logarithm, then we'll solve the exponential by applying the logarithm. That's our overall goal throughout this entire unit of material. So let's work at finding some inverse functions. Now I'm going to start off with a really simple one, then we'll get to a more complicated one. The simple one that I want to find the inverse of is x plus 3. Now we should know the answer to this already, that we know that to undo adding 3 to something, we should subtract 3 from something. So we know ahead of time that our inverse should be x minus 3. But let's walk through the steps. What I want you to do first is just to make sure that we're using the same terminology and everything. We're going to say, instead of f of x, let's write y equals. So let's write this as y equals x plus 3. No big whoop there, just so we're writing in x's and y's. We know that f of x means the same thing as y. Now step 2, and this is really important. Most of the time in math, every step that we do is equivalent to the step above it. And so we just shouldn't be changing anything. We're just rewriting it in some way, shape, or form. Step 2 in this process that I'm writing down is actually changing things. So what I like to do as far as my organization is I like to write down the word inverse. Here's where I'm actually finding the inverse. We find the inverse by just flip-flopping x's and y's. Anywhere that you see a y, replace it with an x. Anywhere you see an x, replace it with a y. And that's it. Because that's how we define what an inverse is. If xy is on the function, then yx is on the inverse, so they're just flip-flopping. So that's all we're doing here. Then we want to try to write this eventually as f inverse of x equals. We want to write it in function notation, which means we want to get the y by itself. So we're going to subtract the 3 to the other side. That's step 3. Step 4, replace the y with f inverse of x. Because that's just the name of it. The name of this inverse function is f inverse of x. So instead of y equals, we can say f inverse of x equals. And that's our answer. So let's look at a little more complicated problem. Our steps are going to be the same, though. We're going to start off by saying, hey, let's just write this as y equals instead of f of x equals. So there's step 1. Now in step 2 is where I'm actually going to change something. So I'm actually finding the inverse. This is not equivalent to the step above it. I'm actually changing it. I'm flip-flopping x's and y's. Now I have the actual inverse. It's just not written in a way that I like it. So in order to write it in a way that I like it, I want to get the y by itself. So in order to get the y by itself, we don't like the fact that the y is in the bottom right now. So what I want to do first is I want to clear my fractions. You know, fractions suck, get rid of the fractions. So I'm going to multiply both sides of the equation by y plus 2. Oops. On the right-hand side, the y plus 2's divide out. Then I want to write what's left because we kind of have a couple different approaches that are going to look different but be equivalent. So I'm going to write where we're at right now. We have x times y plus 2 on one side and 3 on the other. I'm going to write this twice because I'm going to solve this problem in 2 different ways just to point out that there's 2 approaches you can take, and you can go ahead and do whichever one you like better, but to realize that they are equivalent. So on the left side, one thing that I could do here is say, let me distribute that x throughout. That's going to give me xy plus 2x equals 3. Now remember what your goal here is, that your goal is to get the y by itself. So anything that's not a y, we basically just treat like a number and say, all right, that guy right there, that 2x, treat him like a number. Subtract him to the other side. So the next thing is 3 minus 2x, or if you want to write negative 2x plus 3, whatever. Now to get the y by itself, we could divide both sides of the equation by x. That's going to get me y equals, which is what I wanted, 3 minus 2x over x. And then instead of y equals, we have f inverse equals. There's one answer. Now the other direction we could go, so going back up to the step that we had x times parentheses y plus 2 equals 3, the other thing we could do in order to get the y by itself is we could have divided by x at this step. Is we could have said, let's get the x out of there. That's going to leave us y plus 2 equals 3 over x, and then we could subtract 2 from both sides. Then instead of y equals, we have f inverse equals. Now, both of these are equivalent to each other. Both are 100% correct answers. Now, I do bring this up, though, because on a multiple choice final exam, for instance, you need to recognize that they're equivalent. So, for instance, from our first one on the left, if I were to distribute the x into both sides, then this becomes 3 over x minus 2, and we can see it's equivalent to the other one. Whereas if we have this one here and say, hey, if I want a single fraction, I would need to multiply by x over x to get a common denominator, we can see that he's equivalent to the other one. So two different approaches to the same problem. Both work perfectly fine and both are correct. So let's talk a little bit about graphing. Now, we know that if AB is on the graph of a function, like we have our blue function here, we've got some ABs on it. For every AB on the function, we know that BA will be on the inverse. So A2, B2 is on the function, B2, A2 is on the inverse. Now, because we know this, we know that the function in the inverse will actually be symmetric with respect to the line y equals x. Now, we can look at exactly why this is the case. We know that in order for this to be the case, their distance from the line y equals x has to be the same. The line between them has to be perpendicular to the line y equals x, which we can definitely prove. We can find the slope between a3, b3 and b3, a3. The slope between them is b3 minus a3 over a3 minus b3. All that's different is the order of subtraction, so that's a slope of -1 every time, not just for this particular situation. So this shows us, and we could show that the midpoint of these is in fact y equals x as well. So not too terribly hard to show that the midpoint between those 2 points, so if we take a3, b3 over 2, and then it would be a3 plus b3 over 2, that midpoint is actually on the line y equals x because those two values are the same. So we have this symmetry with respect to the line y equals x. Now I bring this up because it helps us to identify if we've made a mistake or not. It also helps us to say, if our function crosses the line y equals x, like it does down here, the inverse will as well. And hopefully that's clear, because if an ordered pair like 2, 2 is on your function, when you flip-flop it, 2, 2 is on the inverse. So that's just a basic overview of the idea of a graph, and then we're going to get into actually graphing some inverses. One thing that we're going to do with graphing inverses, we're going to say, given the function's graph, can you graph the inverse? And the idea of this is hopefully straightforward. We got this function f that's a solid line. What I want you to do is I want you to identify a couple ordered pairs that you can clearly see are on the function. So our function f clearly has the ordered pair 3, 3. It clearly has 2, 1. And it clearly has 1, -1. This helps us because then we can say, what ordered pairs does my inverse have? Well, just flip-flop them. 1, 2, and -1, 1. So if I now plot those three ordered pairs, we have 3, 3, we have 1, 2, we have -1, 1, and when I connect those dots, sure enough, it looks like we have symmetry with respect to that dotted line. So if you're given a graph and you're asked to find the graph of the inverse, we basically just find ordered pairs that are on the graph f and then just flip-flop them. And that's all you got to do. The last topic I want to talk about in this lesson is sometimes we're going to be asked to show that functions are inverses of each other. Now, in order to show that two things are inverses of each other, what you really want to do anytime you're asked to show something or prove something is you want to go back to the definition. And really the best definition is to say that two things are inverses if both of these things that I've boxed in are true. If doing f followed by f inverse gets us back to where we started, and doing f inverse followed by f gets us back to where we started, then they're inverses. So that's what we want to prove, is we want to prove that if I do f inverse of f of x, then I'm hoping that I eventually get down to just x. And if I don't, then they're not inverses. But I also want to prove that f of f inverse of x will also eventually get me down to just x. That's my goal. So basically what this problem amounts to is two different composition problems. For this first one, we have f inverse of 3x plus 2. What does f inverse tell me to do? F inverse tells me whatever you're plugging in, subtract 2, and then divide that by 3. What is it that I'm plugging in? 3x plus 2. Well, if I have a plus 2 and a minus 2, that adds up to 0. And 3 divided by 3 leaves me with just x. Now, hopefully it's important to notice that because we're trying to show something, we can't be doing work in our head. We have to be showing our work because that's the whole purpose of this. We knew that we were going to get x because we were told we were going to get x. We were told these things are inverses. So it's important to show every single step. And similarly here. So for f of f inverse was x minus 2 over 3. The function f tells me to do 3 times whatever I'm plugging in plus 2. And what I'm plugging in is x minus 2 over 3. Our 3's divide out, leaving x minus 2 plus 2. Minus 2 plus 2 adds up to 0, leaving just x. So that's how we'd prove or show that two things are in fact inverses of one another.